Hi everyone. Through this class, we are going to study about the different ways of specification of a digital IIR filter. Let h of e raised to j omega equal to frequency response of IIR filter and modulus of h of e raised to j omega equal to magnitude response of IIR filter. The magnitude response of IIR filter will have a pass band, a transition band and a stop band. The specification of IIR filter can be expressed in any one of the following three different ways. Case 1, gain at pass band and stop band edge frequency. Case 2, attenuation at pass band and stop band edge frequency. Case 3, ripple at pass band and stop band edge frequency. In case 1, while designing a low pass filter, we want to specify gain at pass band and stop band edge frequency. The gain can be expressed either in normal values or in decibels. The maximum value of normalized gain is unity, so the gain at band edge frequencies will be less than 1. Therefore, the dB gain will be negative. Let omega p equal to pass band edge digital frequency in radians per sample and omega s is stop band edge digital frequency in radians per sample. Then AP equal to modulus of h of e raised to j omega at omega equal to omega p, that is the gain at pass band edge frequency or magnitude gain at pass band edge frequency. AS is modulus of h of e raised to j omega at omega equal to omega s, that is gain at stop band edge frequency. And AP in decibels equal to 20 log modulus of h of e raised to j omega at omega equal to omega p. And AS in dB is 20 log modulus of h of e raised to j omega at omega equal to omega s. This is the dB gain at stop band edge frequency. The gain in normal values can be converted into dB gain and vice versa using the equation AP in dB equal to 20 log AP and AP equal to 10 raised to AP in dB divided by 20 and AS in dB equal to 20 log AS and normal value of AS equal to 10 raised to AS in dB divided by 20. The magnitude response of digital IIR low pass filter is like this. Here the modulus of h of e raised to j omega is plotted with this omega. Then we can see that the maximum gain it is marked as 1 and the pass band edge frequency it is marked as omega p. Stop band edge frequency it is omega s. And the gain at this omega p that is AP and gain at this omega s that is AS. Suppose AP equal to 0.8 and AS equal to 0.2, then the gain in dB at passband edge frequency that is equal to minus 2 dB and at stop band edge frequency it is equal to minus 14 dB. So this is the log magnitude response. Here we plot the log value of h of e raised to j omega, that is in dB gain in y-axis versus omega. Then we get the graph like this. And here we can see that the pass band edge frequency is noted as omega p and stop band edge frequency is noted as omega s and dB gain, maximum gain is 1. So dB gain when we take at that maximum value it is equal to 0 and at pass band edge frequency and stop band edge frequency gain is negative. And here we can see that AP equal to minus 2 dB and our AS in dB that is equal to minus 14 dB. Next is our case 2. Alternatively, this specification of filter can be attenuation at pass band and stop band edge frequencies. The attenuation in normal values is inverse of the gain in normal value. The attenuation is usually expressed in decibels. Since the gain at edge frequencies are less than 1, the attenuation in normal values will be greater than 1 and the dB attenuation is positive. Let alpha p, that is attenuation at passband edge frequency, that is equal to 1 by AP, that is equal to 1 by modulus of h of e raised to j omega at omega equal to omega p. And attenuation at stop band edge frequency, that is alpha s equal to 1 by as, that is equal to 1 by modulus of h of e raised to j omega at omega equal to omega s. And alpha p in dB is 20 log 1 by AP, that is 20 log 1 by modulus of h of e raised to j omega at omega equal to omega p. And attenuation at stop band edge frequency in decibels is alpha s in dB equal to 20 log 1 by as, that is equal to 20 log 1 by modulus of h of e raised to j omega at omega equal to omega s. The attenuation response of digital IIR low pass filter is like this. Here the attenuation alpha is plotted with omega. And the attenuation at passband edge frequency omega p is alpha p. And the attenuation at stop band edge frequency omega s is alpha s. Alpha s and alpha p are positive. And the dB attenuation versus omega is like this. Here the dB attenuation at stop band edge frequency omega s is alpha s in dB and the passband edge frequency is omega p. Attenuation corresponding to this omega p is alpha p in dB. This alpha p in dB and alpha s in dB are also positive. Next is case 3. Sometimes the specifications are given in terms of ripple or tolerance in the passband and stop band. Passband ripple is represented as delta P and the ripple in stop band by delta S. And delta P in dB is 20 log delta P and stop band ripple in dB is 20 log delta S. The dB ripples can be converted into normal values by delta P equal to 1 minus 10 raised to minus delta P dB by 20, whereas delta S by 10 raised to minus delta S dB by 20. The ripples in normal values can be converted into gain or attenuation as AP equal to 1 minus delta P and AS equal to delta S. Whereas alpha P equal to 1 by AP, that is equal to 1 by 1 minus delta P. And alpha S is 1 by AS, that is equal to 1 by delta S.